All right, class, since today's lecture did not process correctly, I just want to finish out Chapter 6 so you have some information. You may want to look at the Tuesday lecture as well. I know there's not audio for the first part, but there is audio for the second part of that lecture, so you may want to look at that as well. So what we're going to do today is pick up where we left off. We've talked about the quantum numbers N, L, ML, MS, and today what we're going to do is look at how that translates into electron configurations. Electron configurations are how we assign where the electrons are in relation to the nucleus based on the quantum numbers. So we're looking at a mini electron system. We're not looking at a one electron system where the sublevels are degenerate. We talked about that the last time, that if the sublevels like S, P, and D are all the same energy, we say that they are degenerate. But in a multi-electron system, the sublevels L equals 0, L equal 1, L equal 2, they have different energies, and so we lose that degeneracy. We're also going to talk about some principles as we build up the electron configurations, the Pauli exclusion principle. Make sure you can apply the definition of the Pauli exclusion principle, not just memorize the definition, but apply it to a problem. The Offball Principle, Hund's rule, which tells us that we need to put our electrons in each orbital spin up to maximize the number of parallel spins before we pair them. And then we'll talk about just the general rules for writing electron configurations. So the last time we looked at hydrogen, hydrogen only has one electron. So because hydrogen only has one electron, it does have degenerate orbitals. And the electron normally resides in N equals 1. And N equals 1 N equals 1. The way we write that N equals 1 is the 1s that you see here in the middle of this page. So N equals 1, and then L equals 0. That's the S sublevel. That's this part here. Okay, so N equals 1, L equals 0. That's the only possible value you can have for L, because remember, L takes on the values of n minus 1 and any whole number to 0. That's where the electron normally resides for hydrogen, and that's called the ground state. So you need to know this terminology. Ground state means where the lowest energy, where the electron normally resides. And if it jumped up into the N equals 2 level, energy level, then it would be called an excited state. And what we would see then is the electron, if we look at it this way, here's the nucleus. The electron has jumped up into the N equals 2 level. That's an excited state. We usually put an asterisk there to do that. And then it'll fall back down to where it belongs, the ground state. Oops. And when it does that, it emits a certain frequency of radiation or a certain wavelength of radiation. So that's what we talked about the last time. We're not really, that's not the focus of today. The focus of today is to be able to write the electron configurations for any element on the periodic table, following the rules that we're going to be talking about. So one of the things we've already talked about is that if you have a L equals 0, the sublevel is L equals 0, the probability of where the electron is in a sphere around the nucleus. So a sphere is unidirectional. It doesn't really, if I put this sphere in a magnetic field, I get an ML equal to 0. It's still spherical in probability. But when I go to L equals 1, the probability shape is dumbbell shaped. And this dumbbell shape has direction to it. It's on the z-axis here. It's not on the x-axis. It's not on the y-axis. That would be coming out this way. But it does have direction to it, and that's L equals 1. The probability shape is dumbbell. When I put this a mini electron system that has an L equal 1 sublevel in it, that sublevel splits. And it splits into the same dumbbell shape, same probability shape, but one is going to be on the x-axis, and then the other one is going to be on the y-axis, like so. So I get 3 shapes. And we talked about this the last time. These are called orbitals, and the values are negative L, which in this case would be -1, 0, and +1. And I don't care which one you assign these. Like if you want to say this one's 0, this is -1, this is +1, that's okay with me. We don't talk about which ones get assigned the values in this course. So that's what they talk about, that it splits. Orbitals in a shell split. Well, magnetic means we've put the atom in a magnetic field and the splitting has occurred. All right, this slide shows we don't have degenerate sublevels anymore. The lowest energy is what we see at the bottom here. That's N equals 1. We're on the ground floor. When N equals 1, L equals 0, and ML equals 0. Then we go to the next. Here's something I want to make sure you understand. To go from level 1 to level 2, that's our biggest jump right there. As we move higher and higher up the principal quantum numbers, up here we're up to 5 or 6, and then we have the 4D here. As we move up, notice the levels get closer together. That's important to know. So when we go up to here, we have N equals 2, L equals 0, and that makes ML equal to 0. So the level is N equals 2. The sublevel is represented by the box here. That's L equal to 0. That's the S sublevel. And then inside the box is the ML equal to 0 orbital. And then if N equals 2, we also have the value of L equal to 1. Well, L equals 1 is a little bit higher in energy in a multi-electron system. And so that's the P designation. Remember SPD, that's the letter designation for L equals 1. And yes, these 3 orbitals are, so each box represents an orbital. And these orbitals are degenerate. And they are the dumbbell shapes that we just saw. One on the z-axis, one on the x-axis, and one on the y-axis. And one of these is -1, one of these is 0, one of these is +1. So the other thing you notice is how it fills up. We go from the 1s to the 2s to the 2p, then we fill up the 3s, then we go to the 3p, and then the shocker here is we fill up the 4s, that's a higher N value, before we fill up the 3d. And what's going to help us here is looking at the periodic table. So you want to look at the periodic table to help guide you through the process of filling up these orbitals. So the first rule we have is called the Pauli exclusion principle. And the Pauli exclusion principle says that no 2 electrons can have the same 4 quantum numbers. They can have the same 2, or same 3, but they can't have the same 4. So for example, we've talked about hydrogen plenty of times in this class. You know that hydrogen has one proton and it has one electron. And that one electron resides in n equals 1, L equals 0, ML equals 0. And then we said that the first electron that goes in an orbital always goes in spin up, like that. So that's the spin quantum number, and clockwise to the magnetic field is what we generally go by convention. And clockwise to the magnetic field, we're going to assign a positive 1/2. So the spin up here represents, this electron can be represented by those 4 quantum numbers, 1, 0, 0, positive 1/2. Well, the next element on the periodic table is helium. Helium's in the same period, the same horizontal row as hydrogen, and it has 2 protons, and it has 2 electrons in the first shell. So it looks just like hydrogen, but now we put an electron here, spin down. And that's what the half a arrowhead means here, spin down. So its quantum numbers are 1, 0, 0, negative 1/2. So these 2 electrons have the exact same 3 quantum numbers, but they don't have the exact same 4, and that's what the Pauli exclusion principle says. Only one electron in an atom has a set of 4 particular quantum numbers, unique quantum numbers. So only one electron in any given atom can have, each electron has a unique set of 4 quantum numbers. And that's what the Pauli exclusion principle is all about. No 2 electrons can have the same 4 quantum numbers. That's what we generally say. All right, so let's go to the next slide. The next slide, again, continues on, that says 2 electrons in the same orbital have paired spins, but they have to be in the opposite directions. All right, this slide points out the difference between an orbital diagram and a electron configuration. So this is called an orbital diagram. We know that hydrogen has 1 proton and 1 electron. Where does the 1 electron reside? Well, it resides in the lowest energy level, n equals 1. If n equals 1, the L value has to be equal to 0, called the sublevel. The sublevel gives us what the shape of the probability looks like. That would be spherical in shape. When we place it in a magnetic field, the ML value for this electron is going to be 0. That's called an orbital. And in that orbital, there's an electron spinning clockwise to the magnetic field by convention, and we give that the number positive 1/2. So an orbital diagram is a picture. You can see very easily the L, the N, the L, the ML, and then the MS, and you can see that the electron is spinning clockwise to the magnetic field. You can also see that for helium, all that happens is we add another electron to the orbital, has the same 3 quantum numbers, but the 4th one makes this one negative 1/2. So orbital diagrams are important. They show visually very quickly what's going on. But the problem with an orbital diagram, it takes a lot of time and space. So we look for a more compact way to write what we see here, and that's called an electron configuration, where the number out in front is N, the S value is the sublevel, that's the L value, the angular momentum, that tells us the probability shape, and then the 1 here denotes the orbital or the subshell. So it's really a combination. The orbital is the ML value, the subshell is the L value, so it has both implications there. So ML is this shape in 3-dimensional space, but remember this is unidirectional in 3-dimensional space, so there's no splitting here. So you have to be able to write both orbital diagrams and electron configurations for the elements on the periodic table. Overall, this one becomes the most important, the electron configuration, which we may just say EC for short, because it's compact and easy to manage. So here are some of the, let's see. Well, I skipped one here. All right. So we've talked about the Pauli exclusion principle. The next principle that you need to understand is called the Offball Principle. Offball. So the Offball Principle says that when we add electrons to an atom, we always start from the lowest energy and we build up to the highest energy. And so that's why they call the Offball Principle the building up principle. It's kind of like you start at the foundation and work your way up the building. And so that's what you're going to see in every electron configuration. We must fill the lowest energy first before we move to the next energy and then the next higher energy. So we don't skip around. We start from the lowest energy and work our way to the highest energy. So for example, if we look at lithium, so have your periodic table out if you don't have a periodic table out. Let's look at lithium. So we have in previous lectures been able to write that lithium, if I look at the isotopic symbol, it looks like this, lithium 7 with the 3 here. We're focused on the 3, that's the atomic number. That tells us this lithium has 3 protons and it has 3 electrons, and for it to be electrically neutral. So when we look on the periodic table, we notice that lithium is not in the first row of the periodic table, it's in the second row, the second period. And so that is reflective of N equals 2. So lithium is the first element in the second period. So what we have here is we have 3 protons. We have the first energy level and we have the second energy level. There are 2 electrons in the first energy level and 1 electron in the second energy level. So this is called an atomic diagram, and if you're ever stuck, it's worth drawing an atomic diagram. Just draw you a quick atomic diagram. It tells you how many electrons is in each shell. 2 in the first, 1 in the second. Where are the 2 in the first? Well, highly detailed, it looks like this, the electron configuration. N equals 1, L equals 0. You have 1 electron in the orbital spin up, that's a positive 1/2, and you have 1 electron in the orbital spin down, negative 1/2, and that's all that orbital can hold, is 2 electrons. 1 spin up, 1 spin down, that's it. I don't care where the orbital is in the electron configuration, an orbital can only hold 2 electrons. So the periodic table tells you, hey, you got to go to the second level now to get to lithium. So that's N equals 2. When we're at N equals 2, we have 2 sublevels, L equals 0, L equals 1. Well, L equals 0 is lower in energy than L equals 1, so we draw this box to represent the ML value equal to 0 for L equal to 0 here, the 2s. So this orbital can only hold 2 electrons, 1 spin up, 1 spin down. We only need the spin up one because lithium only has 3 electrons. Here are the first 2 in the first energy level and 1 electron in the second energy level. So what you're going to find out on the periodic table is groups 1 and 2, after we get to the second period, they always fill up the S sublevel. Groups 1 and 2, the vertical columns 1 and 2, called groups, always fill up the S sublevel. So right next to lithium is beryllium in the second period. Beryllium has 4 protons. It has 4 electrons. Where do those 4 electrons reside? Well, the first 2 reside the same place lithium's does, in the 1s2. Then Offball says you got to build that up, so the next lowest energy is the 2s. And so we're looking at the 2s. There's lithium's electron, or there's lithium's electron, and then there's beryllium's electron spin down, and that's all the 2s orbital can hold. Remember, N equals 2, L equals 0, ML equals 0. Again, L equals 0 is S, and then you only have 1 orbital called the S orbital, and that orbital can only hold 2 electrons, 1 spin up, 1 spin down, and we're finished with beryllium. Now, the periodic table tells you, hey, something's going on, because once you go from beryllium, you jump all the way across the periodic table over to group 13. You don't do groups 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You jump all the way over to 13. So that tells you something's happening. So the next element on the periodic table is boron after beryllium, and it's in group 13. And boron has 5 protons, and it has 5 electrons. So where does the 5th electron go? Well, the first 2 go just like helium. Second 2 go just like beryllium. And now the 5th electron goes into a new sublevel, the p sublevel. So what we're doing here is n equals 2, L equals 1, because the zero's filled up. We already taken care of L equal to 0 when we did the 2s2 here. Now, when L equals 1, we get 3 ML values, 3 magnetic quantum number values. We get -1, 0, and +1. Oh, that right here they are. -1, 0, +1. So there's our 3 orbitals. The first electron, by convention, Offball principle, is always in the orbital spin up. So there's my 5th electron to go with the 5 protons in boron. All right. So that's called an orbital diagram. You can see this is getting to be a lot of work. So what we like to do is write it this way, in a more compact fashion, called an electron configuration. So here's orbital diagram. Over here, orbital. Over here, we'll just say EC for short. Tells us exactly where the electrons are 90% of the time. Remember, it's a probabilistic model. We only know where the electron is 90% of the time. It's not in an orbit. It's somewhere in that 3-dimensional space around the nucleus. Now, what I expect you to be able to do before we move on, if I ask you to tell me what the 4 quantum numbers are to describe that electron, you should be able to write the 4 quantum numbers to tell me where that electron, to tell me about that electron. So you would say n equals 2, L equals 1, because it's a p sublevel. ML, you can say any of these numbers and it can be correct. -1, 0, +1. We don't assign the actual value of p of the orbital for this. So you just choose one. I'm going to say -1 because that's what I've got it labeled here. And then the last quantum number, the magnetic spin quantum number, because it's always, first electron's always by convention clockwise to the magnetic field, we say a +1/2. So you have to be able to do that. I pick any electron in an atom. You tell me the 4 quantum numbers that describe where that electron is 90% of the time. All right, let's go on to the next one, which is carbon. Okay, so we see a new rule here called Hund's rule. So Hund's rule says you add electrons that maximize the number of parallel spins, or in this case they say same spin, but technically it says maximize. You place electrons in an atom to maximize the number of parallel spins. What does that mean? So carbon has 6 protons and it has 6 electrons. And if I did an atomic diagram, I'd have 6 protons, I'd have 2 electrons in the first shell, and I would have 4 electrons in the second shell. And so 2 of those electrons in the second shell have been taken care of already. So where do the other 2 go? Well, some people that haven't had any chemistry, they may want to put the 2 electrons together like that and not have this electron here. That would be incorrect. Hund's rule says that each electron wants to be in its own orbital to maximize the number of parallel spins. Now, it makes sense. Let's talk about it. If the dumbbell shaped is what L equals 1 looks like, the 2p looks like. And when we put it in a magnetic field, it splits into 3 of these shapes. One along the x-axis, one along the z-axis, one along the y-axis. And we know that like charges repel each other. That's a common thing in physics. We always should know that. Like charges repel each other. Then each electron will want to be in its own three-dimensional space before we have to pair them together to minimize electron-electron repulsion. So what we need to do is what we saw, and that is the electron does not go and does not pair with the other electron in the 2p. It takes its own position, its own orbital. So when you see 2p2 here, what you should be thinking is, oh, the p orbital, there are 3 of them, 1, 2, 3, and each electron will go in its own p orbital before you pair them. So nitrogen's next. Nitrogen has 7 protons, 7 electrons. There's 2, there's 4, and then it's spin up, spin up, spin up. Each electron goes in its own orbital to minimize electron-electron repulsion and to follow Hund's rule. So you need to know Hund's rule there. You go, why do I need to know this? Well, elements that have unpaired electrons tend to interact with the magnetic field much more strongly than something that's all paired. Usually paired electron atoms are diamagnetic. They do not interact with the magnetic field as much as something that has unpaired electrons. So you're going to find when we do iron, you'll see that iron has quite a few unpaired electrons. All right, so we continue on in period 2. So after nitrogen is oxygen, and when we do oxygen, we are forced to pair in what we'll call this the px. Okay, we'll call that px, py, pz. We can do that. We're forced to, or we could say -1, 0, +1. That's the ml values. But we're forced to pair the 2 electrons together. Now you know that's going to happen. If it's 2p4, you know that there's only 3 orbitals in the p sublevel, and so once you put in the 4th one, it has to be paired. Another thing that's really important here, I think it's important to know, is notice in the second shell now we've got a total of 2 plus 4, we've got a total of 6 electrons. If you look at oxygen, it's in group 16. Whatever the group number is for groups 1, 2, and 13 through 18, whatever the number is in the ones place, that's how many electrons you should have in the ground state neutral configuration for that element. So oxygen is in group 16. It should have 6 electrons total in its outer shell. And this is the outer shell because it has the highest principal quantum number. Right next door to it is fluorine. Fluorine's in group 17, so we expect 7 electrons in the outer shell. There's 2, there's 5, that's 7. Right next to it's neon. Neon's in group 18 on the periodic table. Should have 8 electrons in its outer shell. 2 plus 6 is 8. And that's the end of the second period. And we've completely filled it up. Because once you said n equals 2, you told me the L values are 1 and 0. I should say equals there. And we filled up the S, which is L equals 0. We filled up the P. Again, this is ML equal to 0. And this is ML equal to -1, -1, 0, +1. And that's it. That's all of the 2P. So we're going to use the periodic table to guide you to the next element. So the next element on the periodic table is sodium. Well, sodium is in the third period, and that's the start of the third energy level, n equals 3. So use the periodic table to help you either write the electron configuration or the orbital diagram. All right, in summary, electrons will reside in the available orbits of the lowest possible energy. Offball principle. You start from the background and work your way up, from the lowest possible energy to the highest. Number 2, each orbital, which is the ML values, can only hold 2 electrons. One spin up, one spin down. So that's what it says here. Here's an orbital. That's an ML value. Let's say this is ML equal to 0. You can only have one electron spin up and one electron spin down, and that's it. This is really a different way of saying Pauli exclusion principle. Number 3, electrons will not pair in degenerate orbitals if an empty orbital is available. So what they mean here is when we look at the p sublevel, there are 3 orbitals. There is -1, 0, and +1 ML values, and that corresponds to px, py, pz. We see this when we place that dumbbell shaped into a magnetic field. We get 3 of those shapes, one along the x-axis, one along the y, one along the z. And this is saying that electrons will not pair. They will go in their own orbitals first before we pair them. So this is just another way of stating Hund's rule. And then orbitals will fill in the order indicated by the following figure. All right, so what do they mean here? I don't think you really need to focus on this. I think that you're always going to have a periodic table when you're taking the exam. And if you'll notice, the periodic table fills up the same way. But if you want to write this down as a mnemonic, you can. And pretty much all you do is you write your levels down. You go, here's my first level, here's my second, here's my third, fourth, fifth, sixth, seventh. And then you go diagonally through them to see what fills up. So the 1s fills up first, then the 2s, then the 2p3s, then the 3p4s, then the 3d before the 4p, before the 5s. So either way you want to do it, doesn't matter to me. I think the periodic table pretty much handles this for you. All right, since I'm just lecturing here to make up for the one today, we're going to skip the sample problem. We can look at it. You can try it out if you want to. So you may want to, maybe you should have stopped the video there and try it out for yourself before we move on. So again, calcium, the only thing I will say about the trick for calcium is just make sure that you, when you look at the element calcium, I think it's important to look on the periodic table and go, well, calcium's in the second group on the periodic table, and it's in the 4th energy level or the 4th period. So I know in the end, this is what the ending of my calcium should look like, 4s2. And then I got to start with start at hydrogen, and I build my way up to this ending here. So if you do it that way, you'll probably get the right answer. But that's generally what I look at. I focus on where am I going to end up first, and then how do I get there? From starting with hydrogen's electron and moving this way up through the periodic table, how do I get there and how do I write it? So again, electron configuration up here, orbital diagram down here. Do you need this? No, I think the periodic table will do fine for that. All right, electron configurations in the periodic table. So what you're going to use to do the rest of this chapter is the periodic table. And another thing that we're going to be using is there is a shorthand way of writing electron configurations called the noble gas core. So sometimes your problem asks you for the full electron configuration, and sometimes you can get away with the noble gas core. So the way this works, let's look at potassium here. Okay, so write this down on your paper. Write down potassium. Write down the electron configuration. All right. Notice this way of writing it here. Let's go to the next slide. So if we were doing the full electron configuration, you would look at potassium and go, oh, okay, it ends in 4s1. So how do I get the 4s1? Well, I do 1s2. That gets me from hydrogen to helium. Then I do 2s2. That gives me lithium and beryllium. Then I come over here, group 13. We jumped all the way from here over to here. That tells me something weird's going on. That's because we're going from L equal to 0 over here, the S, to L equals 1 over here called the P. So notice these first two groups, groups 1 and 2, fill up the S except for the first period because hydrogen and helium fill up the 1s. But groups 1 and 2, we generally call this the S block. All right. Groups 13 through 18, we generally call the P block. And then groups 3 through 12, we call the D block. This is L equals 2. This is where L equals 2 comes into play. So when we get to boron here, we're starting the 2p, and we go spin up, spin up, spin up, and then we go spin down, spin down, spin down, and that fills up the 2p6. Then we go from number 10 to number 11, that's sodium, so that starts the third period, third energy level. And again, the first two groups always fill up the S. So sodium, magnesium gives me 3s2. And then we go, again, 3p. Spin up, spin up, spin up, spin down, spin down, spin down. And that gives me 3p6. All right. And now we get to potassium, and it ends in 4s1, which makes sense. It's the first element in the fourth period. Well, there's a chance to make a mistake writing this. Maybe you forget and make that a 3p5 or something like that. So instead of writing this all out, we look at potassium and we trace back to the last noble gas that we crossed, which was argon. And so we put argon in brackets, and then we say 4s1. And that's called the noble gas core electron configuration. So you're going to like that much better, but you need to be able to do both. All right. Now, while we're looking at this chart, I want to show you a couple other things, and we're going to talk about them, but look at this. So we did the 4s1, we do the 4s2. Here's where we start to fill in the 3D. So the transition elements, it's in the D block, and the D block is always a period behind the one it's in. So we're in the third, we go back to the third energy level, and we put the first electron into the 3D. So remember the building up principle? They said that you do the, let's go back to that slide just to kind of help you out here. If we go back to this slide and look at the diagonal, you do the 4s here, and then you fill up the 3D. Now, instead of memorizing that, you could just look at the periodic table. You've got to fill up the 4s here before you go to the 3D here. So another thing I want to point out here is there are anomalies, and I'm not asking you to memorize all the anomalies on the periodic table. There's quite a few, but I do want you to know this one. So this would be 4s2. This would be 3d1, 2, 3, 4. But when you look at the electron configuration, it's 3d5 4s1. Why is that? Because the electron that's in the 4s jumps into the 3d. And you go, why does it do that? Well, there's an empty 3d sublevel. There is repulsion between the two electrons in the same 4s orbital, so that gives enough energy for the electron to jump up into the 3d. So you're going to see anomalies in group 6 and group 11. You see it right here. You would expect copper to be 4s2 3d9, and it ends up being 3d10 4s1. And notice that's the case for the silver and the gold. You don't see it down here, but you do see it down to gold. And so the easy way to remember this, these are the coinage metals: copper, silver, and gold, and they all have an anomaly in their electron configuration. Over here in 6, it's just chromium and molybdenum. Once we get beyond period 5, the levels become so close together we don't see that anomaly there. Yes, there are other anomalies on the periodic table. I'm not asking you to memorize those. Only the group 6 and the group 11 am I asking you to memorize. All right, so the next part I find a little confusing in this book and on our periodic table, and that is the lanthanum and actinide series. And I think what I want to do is, I guess we'll look at it here, and I'll try to tell you what's going on. And you may want to let's go back to the other periodic table, and let's just show you what's going on here, because it is problematic a little bit here. Let me erase all of this. Or at least that much. That's enough to erase, probably, and get away with it. All right, so let's look at, this is where it gets a little tricky. So here on your periodic table, if you got that in front of you, you have barium, that's 6s2. Then you have lanthanum. Now it's not even shown here. All you see is the last part of the 4F series. That's why it says 4F14 here. Notice there's a 5D1 here, and there's the 6S2. Same thing down here. You get to radium, and you have, you have 5F14, 6D1, 6S2 when you're at the end of the intertransition series, the second one. So this is hard to see what's going on here. So let's look at the next slide. And I'm still not real crazy about this slide either. Okay, but let's talk about it. So we're looking at the actinide series, all right? Actinide series. So at the bottom of the periodic table, you have francium and radium right there. That's 6s2. Makes sense. It's in the first two vertical. This is group 1. This is group 2. Actinium is in group 3. So notice the 6d1. You're in the transition metals. 6d1 is the transition metals. From actinium, though, you go down below the table if you've got the periodic table in front of you, and then you have thorium. Well, normally what happens here, this would be 6d1, and now this would be 5f1. Now there's an anomaly here, but you don't have to know the anomaly for this. And then notice right next to it, you have 5F2, 6D1 5F2, 6D1 5F3. And this is the intertransition metals, and that's why they all are F. This is the F. This is L equals 3. And in L equals 3, you have these ML values, these orbitals, -3, -2, -1, 0, 1, 2, 3. There's 7 orbitals. So watch what happens here. This goes, actinium is not in the intertransition metal. Thorium begins that. So you have spin up here. There's 1, 2, 3, 4, 5, 6, 7. So that's spin up, spin up, spin up, spin up, spin up, spin up, spin up. And then 1, 2, 3, 4, 5, 6. Let's see, 7. LR. So there's the last of that. And notice that's where it's 5F14 right there. To me, it's a little confusing compared to our periodic table. So I just want you to look at that, think about it. Look at your periodic table, though. You will see all of this is F. This is F actually here. But actinium is part of the 5D. And so that's where we've got a problem there. And I'm not for sure why it's written that way. Maybe they talk about it in the book, but it's not what we traditionally do there. So same thing. So lanthanum is part of the 5D here. But cerium is where it's 4F. So this is part of the lanthanide series. All of this, and then the one beyond that, which is lutetium, so the Lu. All right, so just keep that in mind. There's a little bit of a problem there. It's not a big problem, and I'm not going to be asking you for electron configurations for the intertransition metals because there's so many anomalies there as well. But follow how it works. So what I would expect you to be able to do is I give you lead, PB, and I want you to write the full electron configuration for it, and I want you to be able to write the noble gas core electron configuration for lead. So if you can do that, you're in good shape, and I'll do that in a minute. But so you may want to stop the video here and attempt your electron configuration for lead, and then we'll talk about it here in a minute and see if everybody's on board or not. We've talked about the anomalies. We would expect chromium to be 4s2 3d4. It isn't. It's 4s1. The s electron jumps up into the 3d. We would expect copper to be 4s2 3d9. It isn't. It's 4s1 3d10. I do want you to know the anomalies. What does anomaly mean? It means you have a pattern and now something is not following that pattern. That's an anomaly. And so you're going to see that for group 6 and group 11. Here's an illustration of it, orbital diagram. The advantage of the orbital diagram is you can see what happened here is that you go from this electron was here, and that creates electron-electron repulsion. It jumps up here. It's not that much energy to do that, and now it's got its own three-dimensional space. Down here you go, well, this is still paired. Why didn't it just stay here? There's more electron-electron repulsion, a little bit higher in energy when it's paired here versus paired here. Think about it. The D subshell is cloverleaf shape. There's much more volume for that electron to reside in than the S, which is spherical in shape. All right, there are other anomalies, especially in the lanthanide and actinide series. We're not going to talk about those. All right, this slide just shows, where the different blocks are, and I think it's an important slide. I mean, we've talked about it over and over. So what you want to get out of this slide is that groups 1 and 2 fill up the S, except for period 1 where we have helium fills up the S. But after we get to period 2 and beyond, groups 1 and 2 fill up the S. Groups 3 through 12 fill up the D, and then groups 13 through 18, except for the first one here, fill up the P. And then the F is actually a break. You know, it's in there, right? You do the 5D, you go one into the 5D, and then you go into the 4F, and then you go into you go 6D, then into the 5F. So that's what that's about. It's just a visual to get you to think about the regions in the periodic table and what sublevel or what orbital are they labeled or attached to. Okay, we have another one. I'm going to have you do this one. You can stop the video, try it on your own, and then you can check your answer. And you can use a noble gas core on this. So like it says in the book, I was kind of, anything beyond hydrogen and helium, if you want to use a noble gas core, you can. So just keep that in mind. All right, so that's the end. Let me back it up here because I want to do one for you before we quit here. Let's do this. Let's back this up because I said we do lead. Let's do lead. There's lead in here. All right. So let's clean this up. Let me erase all of this as much as I can so we're not got a lot of stuff going on here. Let's go back to here. Ooh, I don't know if I wanted to do that. That's not what I wanted. Let's see. All right, we're erasing all of this, making it clean. Hopefully that works on that side as well. Yeah. Okay. So what I want you to do is, hopefully you've already written the electron configuration. You stopped and you wrote the electron configuration for lead. So you can see it here. You can see that this is what it looks like. Okay. So if I asked you to write the electron configuration for lead, the first thing I would want you to do is to look at the group number and look at the period. So in the end, lead should end in 6p2. That's where you have to end up. You're in the P block. The P block is from group 13 to group 18. You're too deep into it, 1, 2. So it should end in 6p2. The other thing that I want you to be aware of is the atomic number is 82. When you're finished, there better be 82 electrons in your electron configuration or you've made a mistake. So we're ready to start. So 1s2, that gets me from here to here. 2s2 gives me those two. Again, offball principle, building up principle. Then 2p6, that's what this tells me. We've jumped all the way from group 3 to group 13. We go from boron to neon, that's 2p6. Then we go 3s2, that takes care of these two. We jump all the way across the periodic table, do 3p6. That takes care of these. Then we do the 4s2. Then this is what you got to focus on right here. Now we have the bridge from the S group or the S block to the P block. This bridge called the transition metal. So that's what a transition is, right? bridge is a transition between two land masses. So we got a bridge here. This is the D block. D block has 5 orbitals. 1, 2, 3, 4, 5. So it's spin up, spin up, spin up, spin up, spin up. Now there are anomalies here, so one of those jumps from the S to there. But just in general, spin down, spin down, spin down, spin down, spin down. Again, anomaly here, don't forget that. But when we get finished with that, we have finished up the 3D10. We come here, we're at the 4P6, takes care of all of this. We come down here, we do the 5S2. We do the 4D10 from yttrium over to cadmium. When we come out the other side here, we're in the P block. This is the 5P. We go 5P6. Takes care of all of those right there. Now we're at the 6S, 6S2. Now watch what happens here. So 6S2, and that's why you can't see it here, but the next one is after barium, it's lanthanum, and so we would say 5D1. And then we would go down into the inner transition elements, and we would go from cerium to lutetium, and we would go 4F14. And then we would pop back up here to hafnium. And that would be 5D2. So you notice it says 5D2 there. Now, does that make a big difference? No, because in the end, you're finishing up all of the 5D. So you're going to have 5D10 here. Now, if you want to arrange this as 6S, well, we'll see it in a minute. All right, and then so once we get finished with the 5D, we go back to the 6P, and there's my 6P2 right there. 6P2, so we'll forget that one, but there it is, 6P2. And you're done. Now, you say that's a lot of drawing, it's a lot of error. So then what you can do is you trace your way back to the last time you see a P6, which is right there, 5P6, which represents xenon in the 5th period. And so you put in I don't know where I want to put this. Let's see, I want to try it up here. Just put it. Xenon 6S2. And then here I might just go on and say 4F14. Since it's lower in energy, then 5D10, and then I'm going to finish out with 6P2, noble gas core electron configuration. So that's what you should have. And that's what we have right here, 6S2, 6P2. Notice they have those at the end. So that's okay. So that's it for electron configuration. We're going to spend a little more time on electron configuration in Chapter 7. We're going to look at ions. Why does, one of the things I asked you to memorize previously is that iron comes in a 2 positive form and a 3 positive form. When we were doing naming, we're going to find out why that's the case. We learned that tin, when we were doing naming, comes in a 2 positive form and a 4 positive form. We're going to find out why that's the case. So in the next chapter, we're going to talk about why certain ions, why is it that group 1 always forms positive 1 ion, group 2 forms positive 2 ions. Over here, nitrogen generally forms -3, oxygen -2, and fluorine -1. So now that we know how to assign the electrons within an atom, we can explain why elements form positive and negative ions and the charges on those ions. So that's where we're going with this, and that's what Chapter 7's about. And I'll lecture on Chapter 7 next. Actually, I start tomorrow in my Thursday class, but you'll be seeing videos on that. I hope this helps. I can't stress enough, you need a tutor to help you with this. Thinking Storm Online. You need to schedule office time with me. We're about 3 weeks out from midterm. You need to get Chapter 6 down. If you get Chapter 6 down, 7, 8, and 9 go much easier. But if you don't get Chapter 6 down, it seems like students never gain traction through 7, which is really going to focus on the periodic trends and why things happen. Like, why does the atom get smaller as we go, in general, as we go across the periodic table? Why does the atom get larger as we go down the periodic table? And then we're going to talk about ionization energy, electron affinities, and things like that. It's all about trends on the periodic table in Chapter 7. Hope that helps. Have a good one.